A spacecraft was lost because two teams used different units. A crowded walkway fell after one connection was changed, and engineers warned that a frozen seal could fail before Challenger ever left the ground. These were not unpredictable disasters. Each one passed a moment when someone could still have stopped it. Here are 5 engineering mistakes that should have been caught. The Mars Climate Orbiter survived a 9-month journey through space. It failed at the finish line because one set of numbers meant something different to two teams. NASA launched the spacecraft in December 1998 to study the Martian atmosphere and relay communications for other missions. To enter orbit, navigators had to calculate exactly how each small thruster firing changed its path. One piece of ground software reported those forces in English units. The interface documentation required metric units. The navigation team treated the incoming numbers as metric, so every calculation carried a small error. Small did not stay small. Across months of travel, the mismatch pushed the calculated trajectory away from the spacecraft's real path. On September 23, 1999, the orbiter approached Mars far lower than planned. NASA lost contact as it passed behind the planet. The mission investigation concluded that it burned up in the Martian atmosphere. NASA's review made an important distinction. The unit mismatch triggered the loss, but the deeper failure was that the project's communication, verification, and systems engineering checks never caught it. The spacecraft did what the numbers told it to do. The numbers were wrong. Number 4. The Hyatt Regency walkways. At the Hyatt Regency Hotel in Kansas City, a small change to a steel connection quietly doubled the load it had to carry. The hotel atrium contained suspended walkways. In the original concept, long hanger rods ran from the roof through the 4th-floor walkway and continued down to support the 2nd-floor walkway below it. During fabrication, that arrangement changed. Instead of one continuous rod, the revised connection used 2. One set held the 4th-floor walkway from the roof. A second set hung the lower walkway from the 4th-floor structure. The change looked minor on a drawing. It completely changed the load path. The 4th-floor box beam connection no longer carried only its own walkway. It also carried the 2nd-floor walkway hanging beneath it. The force at the connection was effectively doubled, and the revised detail was approved without the analysis needed to prove it could support that load. On July 17, 1981, a crowd filled the atrium. The 4th-floor connection failed. That walkway dropped onto the 2nd-floor walkway, and both fell to the floor below. The collapse killed 114 people and injured 186. NIST found that critical connections could carry less than 1/3 of the load required by the local building code. This was not an unknowable material failure. It began with one changed connection and a review process that failed to recalculate it. Number 3. The Interstate 35W Bridge. For 40 years, thousands of vehicles crossed the Interstate 35W Bridge over the Mississippi River in Minneapolis. Its most dangerous weakness was invisible from the road. It was built into steel plates joining the bridge's main structural members. Those are gusset plates. At critical nodes, they transfer forces from one part of a truss to another. If they are too thin, the entire load path can become vulnerable. On Interstate 35W, key gusset plates had inadequate capacity because of a design calculation error. The original quality control process did not catch it. Later inspections focused mainly on deterioration in a bridge assumed to have been designed correctly. Over time, modifications added weight. Then, on August 1, 2007, road work concentrated construction equipment and piles of material on the deck while traffic continued through the remaining lanes. At about 6:05 that evening, the main span failed. Roughly 1,000 feet of deck truss collapsed with 111 vehicles on it. 13 people died and 145 were injured. The National Transportation Safety Board found that the undersized gusset plates failed under the combination of the bridge's increased weight, traffic, and concentrated construction loads. The bridge had been inspected, but the system was searching for damage caused by age. It was not designed to rediscover a critical calculation that had been wrong from the beginning. Number 2. Space Shuttle Challenger. The night before Challenger launched, engineers argued that it was too cold to fly. Sections of each solid rocket booster were joined and sealed by rubber O-rings. At ignition, those seals had to respond quickly as pressure built and the joint moved. Testing showed that cold O-rings recovered more slowly than warm ones. The forecast for January 28, 1986, was far colder than any previous shuttle launch. Engineers at contractor Morton Thiokol initially recommended that Challenger not launch below 53 degrees Fahrenheit. They were concerned the O-rings might not seal in time. After a management discussion, the contractor reversed its recommendation. The launch was approved. The Rogers Commission later found that senior decision-makers did not receive the full history of the O-ring problems, the contractor's initial written recommendation, or the engineer's continuing opposition. Challenger lifted off in the coldest conditions the shuttle program had attempted. A joint in the right solid rocket booster failed to seal. Hot gas escaped, damaging the external tank and the booster connection. 73 seconds after liftoff, the vehicle broke apart. All 7 crew members were lost. The physical failure happened inside a small joint. The larger failure happened in the path between evidence and authority. Engineers raised the risk. Management reversed the recommendation. The people making the final decision did not receive the full picture. Number 1. Teton Dam. The first visible warning at Teton Dam was water appearing where it should not have been. The new earth-filled dam in southeastern Idaho held a reservoir about 270 feet deep at the structure. Its compacted soil core and foundation treatment were supposed to stop water from finding a path through fractured rock around the dam. As the reservoir filled in 1976, pressure increased against the structure and its abutments. On the morning of June 5th, workers noticed muddy leakage on the downstream side. The flow grew quickly. Crews used bulldozers to push rock into the developing hole, but water was eroding material from inside the dam. The opening widened faster than they could fill it. Machinery pulled back as the breach became uncontrollable. At peak failure, the Bureau of Reclamation says about 1 million cubic feet of water escaped every second. The reservoir drained in less than 6 hours. Floodwater and debris struck downstream communities, killing 11 people and causing enormous property damage. Official reviews traced the failure to internal erosion through the foundation and abutment system. They also examined the design assumptions, testing, construction, and methods used to control seepage through highly fractured rock. Teton was not an old dam weakened by decades of neglect. It failed during its first filling. The structure reached full-scale conditions before the assumptions beneath it had been proven safe. The disaster became a catalyst for the Bureau of Reclamation's modern dam safety program, created to challenge similar vulnerabilities before another reservoir puts them to the test. Across all 5 cases, the final failure looked sudden. The cause was not. The warning appeared earlier as a unit mismatch, a changed drawing, a thin plate, a cold weather objection, or water moving through fractured rock. The disaster began when the system failed to turn that signal into action. Which of these failures should VillageFive investigate next?